So here's Nettie, the nitrogen molecule, and Ollie, the oxygen molecule, which makes up the vast majority of our area. So every time one of these particles hits and bounces back, that creates, you have to have a force. Why do you have to have a force when it bounces off? Because what are you doing? Are you making the particle accelerate when it bounces off? Yes, okay? It's accelerating because you're changing the direction of the particle. That creates a force. So if I'm holding the end of it shut, you have forces in every direction and it's spherical, right? So the particles are bouncing off, creating a force, boom, there you go. So let's leave the shield out of it for now, okay? Don't worry about the shield. So when I let go, and there's air escaping out the back of the balloon, how does that make the balloon go forward? Sydney.
There's nothing for the air molecules to bounce off on the back
Did
of
you
the
just
balloon?
say air molecules?
Unfortunately, I think I did.
These
The
first
air,
one?
the
How about the
nitrogen and
molecules?
oxygen particles,
Yes, molecules.
there's nothing for it to bounce off in the back.
But there is in the,
For
okay. So look at it this way. When I open this up, these particles are trying to bounce off the back of the balloon. But what happens? There's nothing for them to bounce off of, right?
See.
But are the particles still colliding with the front of the balloon?
See.
See. So now, are they colliding with the sides? Absolutely. But it doesn't accelerate in the side direction because those forces are still balanced. You create an imbalance in the horizontal motion because you have an imbalance in the number of collisions. Okay? Now, look at this in terms of the blast shield. So if there's a blast shield here, Nettie, the nitrogen molecule, bounces out. He leaves the balloon. Now, some people, let's just say, think that, well, that's going to make the balloon go faster because it's going to hit the shield and bounce, which it is. But here's the story. Nettie, the nitrogen molecule, has left the balloon. Okay? He has left the balloon. He's going to hit the shield, and he's going to bounce back. Will that bouncing back in and of itself make the balloon go forward? Has nothing to do with it. If that hits if that hits the shield, that has no influence whatsoever on the balloon. What's the only way that that could influence the balloon?
If that nitrogen molecule was to go back to the balloon.
Yeah, the only way it could happen is if it hit here, changed direction, and went all the way and hit the backside of the balloon. But as soon as I let go of the balloon, what did the balloon do? It left the building. So, did Nettie, the nitrogen molecule, bounce off the shield? Sure. But the balloon had already left. The balloon was already headed down the stream. So, the shield actually has nothing to do with it. Okay? The shield has no influence on it. The whole Newton's third law occurs within the balloon itself. This is what allows rocket engines to operate in space. Because if you look at a rocket engine, okay, when that expels gas, if you had to have a surface for those particles to push against, we could never operate in space because space is a vacuum. But that's why you don't need to have anything back there. The equal and opposite reaction forces take place within the balloon or within the rocket engine itself. Okay, so stop the under camera.